Welcome, good to see you again. In this slice of physics, we're going to look at another example of a circuit. We'll start with a simple circuit with a single bulb and a battery, and then we will add another bulb to it in series and then in parallel, and study the effects of adding this additional bulb as to how it changes the current, the potential difference across the bulbs, and the equivalent resistance of the circuits. And finally, we'll address a question: which bulb glows brighter, the one with the higher resistance or the one with the lower resistance? As you've seen from previous such questions that I've asked, well, the answer is it depends, and we will see what it depends on in this video. So here's our simple circuit that we want to analyze and then add to by adding bulbs in series and parallel. So let's say that this battery here is a 12-volt battery, and the single bulb that's connected to it, let's say, is a 3-ohm bulb. So the current in the circuit will go from the positive end of the battery to the negative end of the battery, so in this direction. And because there's only one resistance and these are ideal wires, the potential difference across this bulb is also 12 volts, the same as the EMF of the battery. And so given that, we can use Ohm's law, which says delta V across a resistor is minus I times R. So in this case, this delta V across this bulb is minus 12 volts, because in the direction of current, that is a drop, so negative, equals minus I times R, which is 3 ohms. And so when we solve this, we get I equals 4.0 amps. And the only additional thing we can figure out is the power of the bulb, so let's go ahead and do that. You'll remember that power was given as I times V, current times potential difference, which we could also rearrange as I squared R or V squared over R. And since we know IV and R, we can use any one of these forms and we'll get the same answer no matter which form we use. Let's just use the first one and say power equals the current, which is 4.0 amps, times the potential difference across the bulb, which is 12 volts as a drop. So the power is 48 watts. That means this bulb will put out 48 joules of energy per second of time. Okay, now we want to see what happens when we add resistances to this in series and in parallel. So our next example is going to be the same battery, the same first bulb, but we're now going to add another bulb in series. And just to take a different number, let's say that we add a 6-ohm bulb to the 3-ohm bulb in series. The battery is still 12 volts, the same thing. So this situation is adding a bulb in series. We want to analyze this circuit, figure out its equivalent resistance, figure out the current through each bulb, figure out the potential difference across each bulb, and see what impact adding this 6-ohm bulb had to the life of the 3-ohm bulb. Okay, first step, we know R equivalent is easily determined when you have resistances in series. It's simply the sum of the resistances. So in this case, it's 3 ohms plus 6 ohms, which would be 9 ohms. So we can replace this circuit with an equivalent circuit with just one bulb that would look like this. So it's a 12-volt battery and a 9-ohm bulb. So analyzing this is pretty straightforward, like we did before. The potential difference across this bulb is 12 volts, same as the battery's EMF. So that gives a current through the bulb of 12 divided by 9, which would be 1.3 amps down to the 2 significant digits that we're working with. By the way, please assume that these resistances were specified to 2 significant digits, so 3.0, 3.0, and 6.0. And as you remember, the current through all the resistances in series is the same. So whatever current goes through the 3-ohm bulb is the same current that goes through the 6-ohm bulb. And once we know that, we can now determine delta V1, which is the potential difference across the 3-ohm bulb, would be minus I times R1, which would be minus 1.3 times 3.0, and that'll give us, when we use the additional significant digits and intermediate numbers, that'll give us a 4.0 volt answer. And when we do that for the second bulb, delta V2, the potential difference across the 6-ohm bulb, we would have minus I times R2, same current, different resistance, so minus 1.3 times 6.0, and once again, when we use the multiple significant digits for intermediate answers, this will give us 8.0 volts. So the 12-volt potential difference between these 2 points gets split as a potential difference across the 3 ohm bulb of 4 volts as a drop, and an additional 8 volts as a drop across the 6 ohm bulb, for a total of 12 volts across both the bulbs combined, which is the EMF of the battery. Lastly, we can get the power of the two bulbs. So P1 would be the current through the first bulb, which is just I times V1 or delta V1, which is a potential drop across that bulb. So this would be 1.3 times 4.0, which will give me 5.3 watts. And P2 would be I times delta V2, which is 1.3 times 8, which is 10.7 watts, or to two significant digits, it would be 11 watts. So let's recap this and summarize what went on. So when we had the 3 ohm bulb by itself, it drew a current of 4 amps from the battery, and it was shining with a power of 48 watts. When we added another resistance in series, its life completely changed. The current through it changed from 4 amps to 1.3 amps. The potential drop across it changed from 12 volts to 4 volts. So now it's not using the entire power of the battery, so to say. It's sharing the battery with the other bulb. And because of that, its power reduced all the way from 48 watts to 5.3 watts. Moving on, let's see what happens when we add a bulb in parallel to the first bulb. So now I got this circuit like this. I've still got the 12 volt battery. I've still got the 3 ohm bulb. And now I want to add another bulb to it in parallel like this, where the two ends are connected by ideal wires, so they have the same potential difference. So let's say I add the same 6 ohm bulb to it. So in this scenario, R equivalent for a parallel is 1 over R1 plus 1 over R2 and the reciprocal of the whole thing, which in this case would be 1 over 3 plus 1 over 6 and the reciprocal. And if you solve this, you would get an answer of 2.0 ohms. So as we said before, the equivalent resistance of the circuit drops when you add a bulb in parallel. Next, we can see what the current through each bulb would be. So the delta V of the battery is 12 volts. So if I have these 2 points over here, A and B, the delta VAB is VB minus VA, which would be minus 12 volts, because I'm taking the lower potential at B minus the higher potential at A. Delta VBA would be a positive 12 volts. Now the important thing is whatever is the potential at A is also the potential here and also the potential here. All of this is ideal wire, so the potential on all of these ends would be the same. And so I can write the potential here as VA, potential here as VA, and same thing on this side. The potential here would be VB and VB. So the potential drop across both the resistances, delta V1 and delta V2, would be minus 12 volts in the direction of current. So that gives me different currents for the two bulbs. So in series, I had the same current through both bulbs but different potential difference. In parallel, I get the same potential difference but different currents. So I would get I1 equals minus delta V1 over R1, which would be minus 12 volts divided by 3 volts. And the two negatives will cancel each other, and I'd get an answer of 4 amps. And similarly, I2 would be minus delta V2 over R2, which would be negative of negative 12 divided by 6 ohms, which would give me 2.0 amps. And when I put these together, the current out of the battery has to be the sum of I1 plus I2 because it splits here at the junction. So this would be 4 plus 2, which would be 6 amps, which makes sense because I had an equivalent resistance of, I forgot to draw that circuit, so let me do it here. The equivalent resistance would be a single bulb that represents both those bulbs, and that was a 2.0 ohm bulb with a 12 volt battery, which would draw a current from it of 12 divided by 2, 6 amps. So all of that ties in. Okay, as a last step, let's do the power. P1 is I1 times V1, which is 4 amps times 12 volts, which is 48 watts. And P2 is I2 times V2, which is 2 amps times 12 volts, that is 24 watts. Okay, let's recap this. So when I added the 6 ohm bulb in parallel, how did the life of the 3 ohm bulb change from when it was by itself? When the 3 ohm bulb was by itself, the current it drew from the battery was 4 amps and its power was 48 watts. And look here, the current still, after adding another bulb in parallel, is still 4 amps and the power is still 48 watts. So its life did not change at all by adding the new resistance. The new resistance, all it did was draw its own additional current of 2 amps. Remember, we said in the previous video that adding resistances in parallel will increase the load on the battery, drawing more current from it. So the battery now has to work harder to supply current to both these resistances. And all of this makes sense. Go back to the example that we talked about. When you have your laptop plugged in and you plug in your iPhone in addition, you don't want your laptop to know any difference. It still needs to operate the same way it was operating. It's just that your power grid has to supply more current to satisfy both the loads it now has. That's how resistances in parallel work. Okay, lastly, I want to now compare the circuit with 2 resistances in series to the one that's got 2 resistances in parallel and see which one is brighter. Well, the one that's brighter is always the one that has the higher power because that's how much energy it's putting out per second of time. So when I have the 3 ohm and the 6 ohm bulbs in series, the one that's got a higher power is the 6 ohm bulb, the one that had the higher resistance. And so when I have bulbs in series, higher resistance means higher power. But when I have resistances in parallel, the answer changes. Higher resistance means lower power. You can see that the 6 ohm bulb only has 24 watts of power, while the 3 ohm bulb has a 48 watt of power. Now, how can that be? Well, let's go back to the definition over here. And we got to be careful when we use these equations. If we want to study the impact of change in resistance on power, this form here seems to suggest that as resistance goes up, power goes up, I squared times R, while the second equation here, V squared over R, seems to suggest that as resistance goes up, power must go down. Well, when we say those statements, we assume that the other factor is not changing. It is true that as resistance goes up, power will go up if current is not changing. Similarly, if resistance goes up, power will go down if the potential difference is not changing. So putting that in context now, when we have bulbs in series, the current through both the resistances is the same. So this is the friendlier form to use when we have resistances in series. And as this equation suggests, higher resistance means higher power. But when we have bulbs in parallel, the potential difference across both the resistances is the same. The current is not the same, so we can't use this. But we can use the V squared over R form because V is the same across both the resistances. So then, as suggested here, as resistance goes up, power goes down, which is what we had here. So let's recap since we covered a few things. In this slice of physics, we started with a simple circuit and saw the effect of adding resistances in series and then in parallel. We saw first that when we add a bulb in series, it changes the current through the original bulb as well as the potential difference across the original bulb. Whereas, perhaps surprisingly for you initially, when we add a bulb in parallel, it does not change anything for the original bulb. It's still got the same current going through it and the same potential difference across it, and hence the same power. Then we looked at the question of when we have 2 unequal resistances in series and in parallel, which one glows brighter? Well, whenever you're discussing the brightness of a bulb, you are looking at the measure of power. So whichever has the higher power will always be the brighter. But in order to tell how that's dependent on resistance, we got to look more closely at whether the current is fixed across the resistances or the potential difference is fixed across the resistances. And in a series circuit, because the current through both the bulbs is the same, the higher resistance bulb is the brighter. But in parallel, because the potential difference across the bulbs is the same, the lower resistance bulb will glow brighter. So in order to figure out the brightness, the best way to do it is to always determine the power, and whichever is the higher number is the one that glows brighter. Thanks. I will see you soon.